Hello everyone, my name is Jinchun Choi. Today, I will present our current research, blockchain-based man-in-the-middle attack detection for photovoltaic systems. Here is a list of the contents that I will present today. Currently, the cybersecurity of PV systems still relies on network-based security postures such as user authentication, firewall, and communication encryption. However, human risks exist, for example, phishing attacks on a specific user. Firewall rules cannot detect the spoofed message or malware. And software vulnerabilities allow attackers to bypass the protection method. Especially, a man-in-the-middle attack can modify critical in-transit data between devices if any system or devices are compromised. A real-time intrusion detection method have been widely studied to detect man-in-the-middle attacks. Using signature or rule-based network intrusion detection, which is detecting irregular network packet format, reply, and message authentication or behavior-based detection using AI. Model-based detection is detecting anomalous behaviors of inverters and PV systems or network traffic patterns. And temporal detection using signal process methods like watermarking. However, intrusion detection for the advanced man-in-the-middle attacks, such as authorized device man-in-the-middle and a third-party man-in-the-middle, has been less studied. In this paper, here are the contributions of our study. We introduced potential vulnerabilities of in-transit data modification by the man-in-the-middle attack in a PV system and propose a blockchain-based man-in-the-middle attack detection method as a countermeasure. Our proposed method utilized a security module attached to OT devices, for example, inverters, gateway, aggregator devices, as blockchain client nodes in the PV system. The proposed mechanism checks the authentication, integrity, and authorization of the in-transit data by using a smart contract which continuously executed hash comparison. This diagram shows a PV system consisting of multiple smart inverters connected to PV panels to supply local loads, common loads, a battery energy storage system, and power to the power grid. The cloud platform, which are the operator's remote center and vendor server, are connected to the PV system gateway through the wide area network using TLS. Although individual smart inverters as TLS clients enable them to directly communicate with the cloud server, a PV system typically utilizes a site data manager that efficiently aggregates and manages multiple smart inverters in the PV system. The multiple smart inverters are connected to the site data manager using the insecure LAN or wireless LAN with a Modbus TCP RTU protocol. We consider in-transit data such as firmware update files and control commands from the cloud server are critical data since they can change the operational condition of the PV system. Here, three potential man-in-the-middle attack cases that can change in-transit data in the PV system. First, wide area network man-in-the-middle. This attack occurred between the cloud platform and the network devices. Unauthorized device man-in-the-middle. The attacker put unauthorized device in the local network to attack field network. Lastly, authorized device man in the middle. In this case, the attacker compromises one of the device in the field. This figure illustrates the concept of our proposed detection method, the blockchain-based zero-trust ecosystem for PV systems. A private blockchain network can collaborate with multi-parties. It can seamlessly handle the user or vendor identified incidents through notification, coordination, disclosure, and validation mechanism. The proposed blockchain platform is designed for zero trust security, which is no network-related entity, including sensitive data, devices, applications, systems can be trusted. The consistent and continuous process of verifying identity, validating activities, and limiting access and privilege will increase the truthfulness of the system security services to ensure the integrity and authenticity of the critical assets. The security modules are attached or installed in the critical devices in the PV system. It will be a software module or an onboard hardware module depending on the resources of the devices. The security module mainly consists of a blockchain client program, intrusion detection system, static malware analysis, and firmware rollback and patch functions. In our research, we focus on the man-in-the-middle detection method using a blockchain-based cooperative in-transit data verification process. This diagram is a proposed blockchain platform for an in-transit control command integrity validation scenario, where the control command is considered as a critical asset. The authentication, integrity, and authorization of the data are keeping verified, and the results are stored in the ledger as security logs. This is an example of a smart contract for the hash comparison between blockchain ledgers and in-transit data received from the security modules. Updates the asset status to normal or modified according to the comparison result. And the algorithm on the right side describes the process of integrity checking for the hashed value of the control command. When the cloud sends a control command, the cloud initializes the process. The security module calculates the hash and updates the blockchain ledger. When the data manager security module receives the control command, it calculates the hash and reports to the blockchain server. After the comparison process with the smart contract, it updates the status of the asset. Following this algorithm, the blockchain will automatically detect a location and device that changes the integrity of the control command. This figure illustrates the real-time HIR security testbed, including a real-time PV system simulator using an OpenRT's real-time simulator. A cyber system testbed using real network system and servers, including cloud and blockchain server, installed in each laptop, and Kali Linux penetration testing tool generating real cyber attacks as real cyber events. A network layer of the smart inverter, a data manager, and Kali Linux attack device are emulated by Raspberry Pis. An inverter security module, a data manager's security module, and cloud security module are implemented in corresponding devices. Based on this cyber system testbed, the penetration testing tools are utilized to evaluate the impact of the malicious cyber event. For the one man-in-the-middle attack, Kali Linux targets the network between the cloud and the data manager. Assuming that Kali Linux is installed in one third-party platform. An unauthorized man-in-the-middle attack is created by sending an unregistered control command by the cloud security module to the data manager through the local network. The authorized device man-in-the-middle attack is conducted by using a customized malware code installed in the data manager emulator, which can modify the control command. For this penetration testing, we use the penetration testing tool in Kali Linux. EtherCap is a tool that provides man-in-the-middle attacks, allowing snipping and modifying the communication data using ARP spoofing. These graphs result from man-in-the-middle attacks in the same malfunction of the PV system. They show the attack impact of the active power and root mean square voltage supplied by inverter. In a normal case, a control command provided by the cloud successfully increased the active power of the inverter by around 50 seconds. However, under the man-in-the-middle attacks, even though the control command was issued by the cloud, the command was interrupted by the attacker. And these figures present the man-in-the-middle attack detection results in the blockchain ledger corresponding to the control command attack by the compromised data manager, which is an authorized device man-in-the-middle. The blockchain ledger clearly shows the blockchain automatically detects the mismatched control command due to the compromised site data manager. Therefore, blockchain-based man-in-the-middle attack detection method can automatically detect advanced man-in-the-middle attacks and provide the security status of assets in the PV system. In this paper, we find a vulnerability of in-range data modification by man-in-the-middle attacks. To handle these threat issues, we proposed a blockchain-based man-in-the-middle attack detection method. Our proposed method utilized a security module that is attached to OT devices in a PV system. Also, distributed blockchain network was involved to build a cooperative data integrity validation ecosystem. Our system can detect man-in-the-middle attack to modify in-range data by keeping tracking of the security logs of the critical assets, which can zero trust for the PV systems. This work is supported by Department of Energy. Thank you very much.